We're ready to finish up this chapter by talking about real gases. As we've gone through the chapter, we've been talking all about PV equals nRT, and it's called the ideal gas law. And not all gases behave ideally. Now, when we call them real gases, we're not meaning that the other ones are fake, real and fake. But real gases sometimes are called just non-ideal gases. Okay, so the last section of your book that we're going to cover says the effect of size and intermolecular force on our molecules. So, an ideal gas, in order to be ideal, it needs to have these two things happening. Number one, they have to have to where they exert no force on each other. That means their collisions are perfectly elastic. If they're on a collision course, they're not going to try to veer away and not collide. If they're on a collision course, but maybe they are just getting close to each other, they're not going to be attracted and collide. They are totally oblivious of each other until they hit and bounce off in a perfect elastic collision. Okay? The other thing that has to be true for it to be an ideal gas is that there has to be the volume of the container is basically empty space. The molecules themselves take up a negligible amount of the volume of the container. So those are things that make them behave ideally. Those are the things that make PV equals nRT work. Okay. So if those two assumptions are not true, we could either say these gases are non-ideal, or we could say they are real gases, okay? That's just historically what they're called. I kind of like calling them non-ideal because it makes it feel like when you call them real gases and ideal gases that there's no such thing as an ideal gas. All right, so let's see when non-ideal gas behavior would happen. What would lead you not to have those conditions? Okay, the first one is a gas has high pressure. Let's think about high pressure for just a minute. You're going to squeeze the volume down, and that's going to raise the pressure up. That's one way that you can bring the pressure up. Now, if you took a whole bunch of gas molecules in your container and they were not taking up space in terms of the empty space between the molecules, and you force them together in a much smaller container, you've got the same number of molecules but in a much smaller space. The distance between the molecules has gotten much, much smaller, and the contribution to the volume of the container is taken up more by those molecules. So the second statement on the previous slide where it said that the molecules have negligible volume in the container quits holding true when the pressure gets high. So any gas that behaves ideally in PV equals nRT applies. If you were to compress it, it's still a gas. But if you were to compress it down and move those molecules closer together, eventually PV equals nRT will not apply. The second thing that causes non-ideal behavior is as you lower the temperature. So when the temperature is high enough, the molecules are buzzing around, bouncing off each other, behaving as gases should. But as you bring the temperature down, you're going to start approaching the point at which it wants to condense and get into the liquid state. Now in the liquid state, they're attracted to each other, right? In the gas state, if they're behaving ideally, they are not attracted to each other at all. But there is this period between being a liquid and being an ideal gas where the molecules are starting to feel a little bit of traction. So they might collide but linger, or they might be on a collision course and they're going slow enough that they'll feel the traction of the other molecule and kind of veer in towards each other. And that will cause it to not behave ideally. So you want them to behave ideally, keep the pressure down, keep the temperature up. Does that make sense? If it's non-ideal, the compression happens, the pressure goes up, or you lower the temperature and it's getting close to wanting to condense, and then it starts behaving as a real gas rather than an ideal gas. Now this equation is van der Waals equation. This is the equation we utilize when it is no longer behaving ideally. In this equation we see some extra terms thrown in. We have P, we have V equals nRT, okay? We see those pieces there. P, V, nRT, okay? But we also see these A, N squared over V squared and NB, all that kind of thrown in. What these will do is take into account two things. The fact that the volume is no longer just empty space, and that the molecules are attracted to each other, and this will kind of put the brakes on the pressure of that container. So what this term does, and where you get the A's and the B's for this, is in tables for those constants, okay? So this is a correction term for the fact that the molecules are attracted to each other. So let's just think for a moment here. A molecule is zipping across and it's going to collide into the wall. So let's draw a wall, okay? Here's a wall. And here's a molecule wanting to collide in the wall. And it's going to collide with a certain force, and it would cause a certain amount of pressure, all the molecules combined banging into that wall. But let's say it's on a collision course and it gets to about right here, and when it gets to about right here, there's another molecule on its path right here that it's attracted to. So it feels an attractive pull to that molecule. What is that attraction to this other guy back here going to do with the velocity at which it's going to strike that? It's going to slow it down. So when it has attractions for other molecules, it will slow down that collision. So if we want to get it back up to what it would be if there was no attraction, we have to add in a correction term. And we see that plus a n squared over v squared, and add in of that term. The other correction term that we have here is going to be a correction for the fact that those molecules aren't just empty space. So when we did V before, it was volume of the container, because we needed the volume of the empty space. Now these molecules are so much closer together and the amount of empty space is not as great, and so we need to subtract out volume due to those molecules, so that's a subtraction term. Now it's very unlikely that you'll actually have to utilize the van der Waals equation in a calculation, but you need to understand what those terms are doing, and you need to make sure you know the fact that not all gases behave ideally and what conditions make them behave in a non-ideal or a real fashion. Now I want to leave you with this graph as the last thing that we talk about in this chapter. If you look at this graph here, what you'll see, and let me just go over to the screen and write on it here for just a moment, that any gas, if the pressure is low enough, as we approach down here to the lowest possible pressure, which would be 0, any ideal gas would have if we had 1 mole of it, okay? This is N, which is equal to PV over RT. If we had 1 mole of that gas, this ratio would be equal to 1. And if it was a true ideal gas at all possible pressures, okay, it would always be 1. But we see that as the pressure goes up, okay, as this is getting bigger and bigger, then the number of the value for that ratio, it's no longer going to be N, it is going to be increasing as time goes by. And so we see a linear increase here, we see it increasing, but we see other cases where it dips down before it increases back up. So those are the different factors taking into place. But as long as the pressure is low, everything, no matter what the gas is, will be behaving in an ideal way. All right, so this ends our chapter on gases and this lesson here. Make sure that you finish up by realizing that not all gases are ideal, not all gases obey PV equals nRT, but for your calculations in this chapter, you're going to assume ideal behavior and you're going to assume that PV equals nRT will apply.